So we have a lot of topics to review, and we're going to get through as many as we can, but you have a test next week on Tuesday, all over from end of chapter 3 at 3.9, talking about inverse trigonometric functions. 3.10 was related rate problems. 3.11 was linearization and differentials. And now we're jumping into, right now, chapter 4, which was optimization and applications of derivatives and graphing derivatives. And so in front of me, or us, we have two graphs. And looking at it, we want to see, is there an absolute max, an absolute min that occurs there? One of each, one or the other, or none. So looking at that first graph, could you tell if there's an absolute max or an absolute min? So there was a theorem that we looked at, the extreme value theorem, but the conditions for the extreme value theorem doesn't hold. We don't have a closed interval that is continuous. And so there's a jump in here. So it's possible that there's no absolute max or absolute min. If we look at this though, there is a value on the graph that has the highest y value. So if I look at x equals a in here, this f of a, this is the highest value, y value on the graph. So we have an absolute min of f of a. So the y value is the min, and the x value is where it occurred at. So at x equals a. So we want to see, is there some value in here that we get the smallest y value? Well, I notice here that it looks like this is the smallest value in here. Let me call this c. The problem is that x equals c is undefined, where it looks like it's getting smaller and smaller. This is an open circle. And so this here, there's no value getting closer and closer to c that would give me a smaller value. Every time I get closer to c on the left, I'm getting closer and closer to this open circle, which keeps on getting smaller and smaller. So in here, there is no absolute min. Oops. And that was supposed to be max. I don't know why I said min up here. This was a max. So there's no absolute min on this graph. So if you look at that second graph, notice it's continuous everywhere, but our interval isn't closed. It's not a closed interval at a and b. A, I'm getting closer and closer to a smallest value, but I'm never ever hitting this f of a value. It's undefined. Same idea here. F of b, I'm getting higher and higher and higher as I get closer and closer to b on this side, but there's no value, y value, that I'm hitting that's going to give me the highest point. And so in this case, we don't have any absolute extrema. So here we're given an equation, and again, we want to see if there's any absolute max or absolute min. And we're given that f of theta is equal to sine of theta plus pi halves. And we want to find any absolute max and absolute min on the closed interval from 0 to 7 pi fourths. So here, because it's a closed interval, I know that sine is a continuous function everywhere, and so it's going to be continuous there. We want to find our critical numbers, and we can find critical numbers by finding our first derivative. So f prime of theta, I notice here that I'm going to have to use the chain rule. So my outer function is the sine, And so if I take the derivative of sine, that's positive cosine of the inner function, which is theta plus pi halves, times the derivative of this inner function. And then derivative of the inner function of theta plus pi halves, well, derivative of theta, that's just 1, and derivative of pi halves is 0. So it's just all times 1. So we're looking at when is cosine of theta plus pi halves equal to 0? You have to remember we're in this interval. So a couple ways we can do this. Maybe let's do a substitution for a second. So maybe I'll let A equal this argument of cosine, this theta plus pi halves. Let's look at when is cosine of A equal to 0. So if I think about this, the values of cosine that give me 0 are pi halves, 3 pi halves, and then I can keep on going with multiple multiples of this. So basically, this is pi halves plus pi k, right? But look at the unit circle. My x value is 0, pi halves, and any plus pi would get me to 3 pi halves. And multiply that by 3, we get, what is it, 5 pi halves, etc. K has to be an integer. That funky z means integer, so k is in the set of integers. And so we know that our value of A has to equal this. Well, A, and we want to solve for theta really. So we're looking at when is theta plus pi halves equal to pi halves plus pi k. Well, if I subtract pi halves on both sides, I get this is when theta is equal to pi times k. But I know theta needs to be contained in this interval from 0 to 7 pi fourths. So if k is equal to 1, this gives me theta is pi. So pi does fall in between 0 and 7 pi fourths. If I let k equals 2, though, I get theta, I'm sorry, k equal 2, I get theta is 2 pi. 2 pi is not contained between 0 and 7 pi fourths. I can let k be negative, but I know, again, this has to be greater than 0, and so I wouldn't even check that. So there's one critical value in between that closed interval. Again, the extreme value theorem occurs here because it's continuous, it's on a closed interval. So the absolute max or absolute min could occur at 0 or 7 pi fourths. So we're going to plug this back into the original function. We're not going to use that first derivative test to see if it's increasing or decreasing. And so I usually just make a table. We have our theta values. We need to look at the endpoints of our closed interval. So 0 and any point in between, that was a critical number, pi, and at 7 pi fourths. So we're plugging those values of theta into our original function, which is sine of pi plus pi halves. Sorry, is equal to theta plus pi halves. So if we look at f of 0, we go in here and we plug in 0 wherever we see a theta, this is sine of pi halves. Sine of pi halves is 0. Sorry, no, it's not. Sine of pi halves is 1. It's equal to 1. So now if we go in and we plug in pi wherever we see a theta. So theta plus pi plus pi halves is 3 pi halves. So this is the same thing as sine pi plus pi halves is 3 pi halves. Well, sine of 3 pi halves is -1. And now plugging in 7 pi fourths. Actually, not 7 pi fourths. Yeah, 7 pi fourths, that's our endpoint. So f of 7 pi fourths. So this is sine of 7 pi fourths plus pi halves. We're going to need a common denominator in here. And so pi halves is the same thing as 2 pi fourths. So this is sine of 9 pi fourths. Well, 9 pi fourths, that's the same thing as 2 pi plus pi fourths. So thinking about our unit circle, if we get to 2 pi, we're going to start repeating itself. So pi fourths. So this is the same thing as sine of pi fourths, which is √2/2. So because we're looking to see what's the highest number and what's the lowest number, if we look at the square root of 2/2, we get that's approximately 0.71. So the highest number that we get back for our y is our absolute max. And so we can see that our absolute max is 1. At x equals 0. And the smallest y value that we get back is -1. And so -1, we have an absolute min of -1 at x equals pi. So find the value or values of c that satisfy the equation f of b minus f of a all over b minus a, which is equal to the derivative evaluated at c in the conclusion of the mean value theorem for the function in the interval. So basically what this mean value theorem is saying is there has to be at least one value c in between our interval, in our case -1 and 2, such that it has the same slope as the average rate of change between those endpoints on our interval. And so if I look at this, f of b minus f of a, this has to be a continuous function in order for this to be true. So if I look at f of b minus f of a, well, let's look at what is f of 2. So if we go back in here, plug in 2 wherever we see an x, we can find f of 2. So we get 2 squared is 4, plus 3 times 2 is 6, plus 1. So we get back 11. So we know we have a point at 211. Let's look at f of -1. So plugging in -1 wherever we see an x. Oops. So we got -1 quantity squared, which is +1, plus 3 times -1, so -3 plus 1. So this gives me -2 plus 1 is -1. So I have a point here at -1, -1. So our f of b minus f of a all over b minus a value, that gives us 11 minus a -1 all over 2 minus -1. 11 minus a -1 is 11 plus 1 is 12. 2 minus a -1 is 2 plus 1, which is 3. And this gives us a value of 4. So we want to find some c that's contained between -1 and 2, such that the derivative evaluated at c equals 4. So first thing we want to do now is we need to find this derivative of our function of f of x. So let's go ahead and do that. So the derivative of f of x, derivative of x squared is 2x, plus the derivative of 3x is 3, and the derivative of 1 is 0. So we're looking at when is 2x plus 3 equal to 4. So if we subtract 3 on both sides, we get 2x equals 1. We divide both sides by 2, we get x is 1/2, which is contained in our interval. And so we're going to say that c, or value in between -1 and 2, that has the same average rate of change of those endpoints, would occur at 1/2. Next. So the next example, we have y is equal to x all times the square root, and underneath the radical is the quantity 7 minus x squared. So it asks us to find where the function is increasing, decreasing, any local extrema, concavity, and to graph this. And so first thing that we need to do is we need to figure out what our domain is. I notice that we have a radical, and it's an even powered radical, so we have to worry about having negatives underneath the radical. And so for our domain, I can see that what's underneath the radical, which is 7 minus x squared, has to be a number bigger than or equal to 0. It has to be a positive number or 0. So kind of think back, I don't know if you remember this, but when we solved inequalities that were nonlinear, which this is, we had to get everything to one side, which is already done. We found critical numbers, kind of like critical points, that set this equal to 0, and then we tested to see if this was above or below the x-axis. If it was a true or false statement. If you look at this 7 minus x squared, when this is equal to 0, there's a couple ways that we can solve this. We can use the square root method, or we could actually factor this. Think of 7 is actually a perfect square of the square root of 7. So we can think of this as factoring square root of 7 minus x, all times square root of 7 plus x. So the values, what set this equal to 0 is plus or minus root 7, which is what we would also gone if we'd done the square root method on this. So let's test. We have a negative root 7, which I know is smaller than 3, and a positive root 7, which I know is bigger than -3, but smaller than +3. So we want to go back in, and we want to see if this number, if we plug it in, is this greater than 0? So let's say we plugged in -3. If we plug in -3 into this piece, I get this is equal to 7 minus -3 squared. So I get this is 7 minus 9, and so this is -2, which is less than 0. So this was a false statement. And so we couldn't have anything less than -√7 as part of our domain. Choose something between -√7 and √7. So if we looked at f of 0, plugged it back into this, we get 7 minus 0 is positive. So this was true. If we plug in a number bigger than √7, so +3, we get 7 minus 9, which is less than 0. This is false. So all that just to tell me that my domain is between -√7 and 7. Okay, so we want to find critical numbers, and we find critical numbers by looking at the derivative. So notice that when we take the derivative of y, we're going to have to use the product rule, and we're going to have to use a chain rule. So let's first rewrite y a little bit so it's a little easier. So this is x all times 7 minus x squared, and that is all raised to the 1/2 power. So we're going to have to use the product rule, like I said. So y prime, the derivative of the first is 1, times the second, might as well just keep it as 7 minus x squared, square root of that, plus the first x times the derivative of the second. So we ought to use the power rule, chain rule too. So here, we're going to bring down our power of 1/2 of the inside, 7 minus x squared, subtract 1 from my power, so 1/2 minus 1 is -1/2, times that derivative of the inside. So derivative of 7 minus x squared is -2x. So notice things kind of clean up a little bit. 2's cancel here. Let's rewrite this. So we have y prime equals the square root of 7 minus x squared. No more 2's. We have an x here times an x here. So we have an x squared in my numerator. And notice that this was a negative, so this will be a minus out front. So x squared in my numerator, all over. Also notice that we can pull down this parentheses raised to the -1/2 power. So pull that down, the square root of 7 minus x squared. Okay, so looking at this and finding out when is y prime equal to 0. So when is 7 square root of 7 minus x squared minus x squared all over the square root of 7 minus x squared equal to 0. Well, we have a fraction. We can clear our fractions by multiplying by our least common denominator, or our denominator in this case, which is the square root of 7 minus x squared. So multiplying on that on both sides of our equation. So notice when we distribute the 7 minus square root of 7 minus x squared to the square root of 7 minus x squared, that's just going to give us 7 minus x squared. Distributing here, we get minus, notice that the square roots cancel. And so we're just left with the x squared equals 0. So you have 7 minus 2x squared equals 0. So if I add 2x squared to both sides, we get positive 2x squared equals 7. We could divide both sides by 2. So we get x squared equals 7 halves. Take the square root of both sides, we get x equals the square root plus or minus the square root of 7 halves. Or the square root of 14 over 2. So we want to see, are those inside our interval or not? I also know where it's undefined. It's undefined where my denominator is 0. So at our endpoints of our domain, so that's okay. So is root 14 over 2 in between negative 0.71 and positive 0.71. So root 14 divided by 2 gives us 1.87. Which is not inside our domain. Which, hold on, I did something wrong. Okay, so I was thinking of this off. This is between approximately negative 2.6 and positive 2.6. And so these values in here, negative and positive 1.87, are inside that interval. And so here we would have a negative, so this was a negative 2.6. And this negative root 14 over 2, this was about, like I said, negative 1 point, let's just say negative 1.9. So we have 1, 2, 3 intervals that we have to check to see if it's increasing or decreasing. And so choose something between negative root 7 and negative 14, negative root 14, and then that all over 2. So something between negative 1.9 and negative 2.65. So how about negative 2? We're trying to find if this is increasing or decreasing. So we want to look at the derivative function. So y prime of negative 2. This is the square root of 7 minus negative 2 squared minus negative 2 squared all over the square root of 7 minus negative 2 squared. Negative 2 squared is 4. And then that's going to be 7 minus 4 underneath the radical. So that's root 3. Minus negative 2 squared is 4 all over root 3. So square root of 3 minus 4 divided by the square root of 3 is approximately negative 0.5. Negative 0.58. Really, I just care that this is less than 0. So it tells me that it's decreasing in here. So choose something in between these two values, negative 1.9 and 1.9. So how about x equals 0? So if we look at the derivative and we plug in 0 wherever we see an x, we get the square root of 7 minus 0 squared over the square root of 7. So this is square root of 7, which is greater than 0, so it's increasing here. Choose something between 1.9 and 2.65. This is where we could have used facts about symmetry maybe to help us, but we didn't, so let's just keep going. So if we plug in 2 here, notice that this is going to give us the square root of 7 minus 2 squared minus 2 squared all over the square root of 7 minus 2 squared. So that gives us the same thing as we had here, root 3 minus 4 over root 3, which was less than 0. So this is decreasing in here. So I can see that we have a min at negative root 14 over 2. And so we could figure out what that value is by plugging it back into our original function. So if I look at y of this, negative root 14 over 2, plugging it in wherever I see an x, so plug it in. I see a square root of 7 minus, I see an x, and that's squared. Okay. Clean it up. So I got square root of 14 over 2 negative. This here is 7 minus squaring a square root. Squaring this numerator, I have positive 14. Square the denominator, I have 4. I'm going to need a common denominator. I notice that this reduces down to 7 halves. So I have 14 halves minus 7 halves underneath the radical. So we have negative root 14 over 2. This is the square root of 7 over 2. So negative root 14 over 2. If I multiply this by root 2 over root 2, that gives me root 14 all over 2. Well, square root 14 times square root of 14 is just 14. So we have a negative 14 all over 4, which is the same thing as negative 7 halves. Okay, so that was the min. Same kind of thing's going to happen when we plug in the max value. When we plug in positive root 14 over 2. The only difference is the sign is going to be changed because of this negative here. So when we look at y of positive root 14 over 2, doing all the work, we should get positive 7 halves. So max at root 14 over 2 is 7 halves. The only thing that we're really missing now is the concavity. If we look at our n values, negative root 7 and root 7, those are the values which set this whole thing equal to 0. It would make this underneath the radical 0 times whatever's in front is 0. So I know those n values are on the x-axis. So we can put part of this stuff together. So if this is -3, this is -2, negative root 7 is about here. We said it was decreasing and we had a min at -7/2, which is the same thing as -3 1/2. And that occurred right at negative root 14 over 2, which was about -1.87. So let's say about right here. And then we said it had a max, right, at positive 7/2 or 3.5. So at 1.89 about, we're going to go up 3.5. And we know that it hits the graph back down here at positive root 7. So all we're kind of missing now is our concavity and any intercepts that we have. So concavity is found by second derivative. So finding the second derivative, let's put down the first derivative. Okay, so finding the second derivative, I pulled up our first derivative, rewriting it so it didn't have the radicals or anything in the denominator. I notice here for the first piece, we're going to use our chain rule, bring our power down front, 1/2, 7 minus x squared, the inside, subtract 1 from our power is -1/2, times the derivative of the inside, which is -2x. Minus, unfortunately here, we're going to have to use our product rule. And so the derivative of our first piece, which is x squared, is 2x. All times the second piece, 7 minus x squared to the -1/2, plus the first, x squared, times the derivative of the second. But the derivative of the second, again, we're going to have to use the chain rule. So we're going to bring down our power, -1/2 of the inside, 7 minus x squared, subtract 1 from our power. That would give us -3/2 times the derivative of the inside, which is -2x. So our 2's cancel. And there, a negative and a negative, that makes that positive. Let's see. And so let's clean this up a little bit. 2's cancel here. So this is a negative. We have an x in the numerator. All over, we can bring this piece down, get the square root of 7 minus x squared. Minus 2x, rewrite this. So this is all over the square root of 7 minus x squared. Plus, that 2 canceled with that 2. We have an x times an x squared. So in the numerator, we have an x cubed all over. This is the square root of 7 minus x squared quantity cubed. Notice here, pretty much our first groupings are like terms. In the same denominator, we have the same variable in the raised to the same power in the numerator. So it's -3x of this. And if we wanted to get a common denominator of these two pieces and this piece, that would be, I'd have to have 3 of those roots. So let's multiply by, I already have one down there, 7 minus x squared squared. The square root of that squared. Plus x cubed all over the square root of 7 minus x squared cubed. Well, squaring the square root just leaves me the radical. So if I just rewrote that piece, it just gives me the radicand. And let's distribute this negative 3x. So negative 3x times 7 is negative 21x. Negative 3x times negative x squared, that's plus 3x cubed. And be careful because I didn't bring down the cube here. The square, that's a cube. Plus this 1x cubed all over our LCD of 7 minus x squared all underneath the radical, and that whole quantity is cubed. So if I did this right, we have 4x cubed minus 21x all over the square root of 7 minus x squared, quantity cubed. So we want to find where this is equal to 0, where it's undefined. It's equal to 0 is fine. Where it's undefined, we have the same thing that we had for the domain, except for the endpoints are also not included here. So we're looking at actually when is our numerator equal to 0? Because if we multiply both sides by that denominator, it would go away. So we could factor out an x if we wanted. So when is 4x squared minus 21, that quantity, equal to 0? So we're looking at x equal to 0, and we're looking at 4x squared minus 21 equal to 0. You can use the square root property by adding 21 to both sides. Divide by 4, so x squared is 21/4. Take the square root of both sides, we get plus or minus the square root of 21 over the square root of 4, which is 2. So the square root of 21, divide that by 2, gives us approximately 2.3, plus or minus. So we want to know, was that in our domain? And we said that negative, positive, and negative root 7 was 2.8. So that is in the domain. And we have to check if it's concave up or concave down. So we have a negative 2.3, we have a positive 2.3, we have a 0, and the square root of 7 again was 2.6. So negative 2.6 about, positive 2.6. So we got to check quite a bit. So choose something between negative 2.6 and negative 2.3. So how about negative 2.5? And if we plug it into this, we want to see, is that going to be a positive number or a negative number? Okay, so 4 times negative 2.5 quantity cubed minus 21 times negative 2.5. That gives me negative 10 in my numerator, all over 7 minus negative 2.5 quantity squared. That's underneath the radical, and then it's cubed. So that is all raised to the 3/2 power, which gives us positive approximately 0.65. So I can see this is less than 0, which means it's concave down in here. So choose something between negative 2.3 and 0. So how about x equals negative 1? So negative 1 cubed is negative. So we have negative 4 plus 21. That's going to give us 17 in the numerator. All over negative 1 squared is 1. 7 minus 1 is 6. And 6 raised to the 3/2 power is positive. This is greater than 0. It's concave up. If we plug in positive 1, we get 4 all times positive 1 cubed. So that's 4 minus 21. That's negative 17. All over positive 6 3/2. So this is less than 0, so it's concave down. Last one, something between positive 2.3 and 2.6. So if we plug in x equals 2.5, we have 4 times 2.5 cubed minus 21 times 2.5. That gave us 10 in the numerator. All over 0.65. So this is greater than 0, it's concave up. So I can see that we have inflection points at negative 2.3, positive 2.3, and at 0. If we looked at when our function was equal to 0, let me restart this. I notice that our function is equal to 0 when x is 0. And so I notice that it's going to be crossing our x-axis. We know that it's decreasing and it is concave. Where did it go? Down. So decreasing, concave down. And then it changes, and then it's concave up. And then it's going to be concave down again. It's going to be concave down. It's concave up until we hit this piece, and it's going to be concave down. Kind of concave downish. Until right before we hit this, it's concave up a little bit. So we got a picture of our graph given that information that we had. So here we have a limit as x is approaching 0 of cosine 9x minus 1. That's all in the numerator, and it's all over x squared. And so first thing that we do when we're looking at limits is we try our direct substitution. And if we do that, we get this is cosine of 9 times 0 minus 1 all over 0 squared. Well, cosine of 9 times 0 is cosine of 0, which is 1, minus 1 in the numerator. So we get 0 over 0, which is our indeterminate form. Doesn't tell us anything, and so we want to go back and manipulate this. We found that there was a rule called L'Hopital's, which says that if this was a continuous function, which it is, then we can look at the, and it's differentiable everywhere, and we can look at the limit, we can look at this limit as x is approaching 0 of the derivative of the numerator. So if I take the derivative of the numerator, so derivative of cosine 9x, well, I need to use the chain rule. So derivative of cosine is negative sine of the inside, 9x, times the derivative of the inside. So derivative of 9x is 9. Time or minus the derivative of 0 is 0, all over the derivative of the denominator. And the derivative of the denominator is 2x. And if we look at this and we do direct substitution again, then I notice again that we're going to get 0 over 0. The sine of 0 is 0. So again, we can use L'Hopital's rule. And we can take the derivative of the numerator. So the derivative of negative 9 sine of 9x. Well, again, we're going to use the chain rule. So the derivative of sine, that's positive cosine, of the inside 9x times the derivative of the inside, which is 9, all over the denominator, derivative of the denominator, which is 2. So as we look at the limit as x approaches 0 of negative 81 cosine of 9x all over 2. Now when we do direct substitution, we get in the numerator negative 81 times cosine of 0, which is 1. So we get negative 81 all over 2, which is negative 40.5. So the limit as x approaching 0 of that function, our y value is getting closer and closer to negative 40.5. But notice that x equals 0 in that function doesn't exist because it sets our denominator equals 0. But a function could not exist at a value, but the limit can exist.